Hello, this is the Mr. Dow Maths channel. Today we're going to be looking at the various numbers of questions that the WJC could ask you based on what we learned before with matrices. The nice thing about these questions are they're quite repetitive, and the different types of questions, albeit they have a lot of variety between them, are usually follow-ups from previous questions, or they're usually standalone questions with just one goal that you have to focus with, and that goal is pretty easy to see. The first type of question I want to look at is a proof question, and it kind of falls into two categories here. It's that you have to show something equals something, or you have to do a proof by induction, which is slightly more complicated, albeit very satisfying way to prove something. We'll look at the first one. Induction, it requires a little bit of prerequisites because it's kind of like a join-in topic for a lot of further maths concepts, and it's a very useful tool, hence why it's taught at the further maths level. So I'm going to say there's a matrix M. So the matrix M is such that M equals A, B, C, D, and M squared equals the identity matrix. Prove A squared equals D squared. This was a 4-mark question, hence why pretty simple, and it should be immediately obvious what you can do over here. Clearly you've been given a matrix, a general 2x2 matrix, and the given information to us is that if you square this matrix you get the identity here. Essentially what it's trying to say is that if I square this matrix, I get kind of like the representative for 1 for all matrices. So let's try and square this matrix. If we have M squared over here, then we're just following on from our multiplication of matrices. So A, B, C, D will just multiply onto itself right here. What you'll get in the end is, if you just follow the procedures from last video, is that you'll just consider every single possibility going row from row and column from column. So kind of looking at it like this. So A squared plus BC for the first element, A times A, B times C, and add together. For the second element, A times B plus B times D. For the third element, A times C, C times A, plus D times C. So AC plus DC. Lastly, you're going to have D squared plus BC. And all of this equals the identity matrix. We're going to choose a 2x2 matrix over here to match the number of elements that we have. And this is the information that we've been given. We've worked out that M squared is this matrix right here, okay? And the proof is A squared equals D squared. Clearly the elements which contain A squared and D squared are elements 1 and 4. But these are the most relevant because they have the identity matrix 1 and 1. Of course you could also try and prove it using 0 and 0, but at least with A squared plus BC and D squared plus BC, there's a foreseeable method in which you can follow, and clearly it's the easier method. So A squared plus BC equals 1 is what we get for our first element. Clearly, I'm just, comparing left-hand side and right-hand side, getting my elements to equal each other. So AB plus BD then also equals 0. AC plus DC then equals 0. And then D squared plus BC equals 1. These two, although you can work with them, I don't think they're relevant with the question, okay? The elements that you really want to be working with are A squared plus BC equals 1 and D squared plus BC equals 1. The key thing you have to notice here is that A squared plus BC and D squared plus BC equal the same thing, 1. Hence, you can actually equate them. A squared plus BC equals D squared plus BC. Now, the nice thing about this is that the BC nicely cancels out. If you subtract BC from both sides, okay, or move BC over, do the inverse operation, however you want to call it, A squared then equals D squared. Hence, this question has been concluded. That is our proof. And obviously you'll have to do a little bit more setup if you want to look at it at a higher level. Obviously this is not really enough. We don't have A, B, C or D defined as what they are, whether they're real, natural, whole. But you can look into that yourself, because the setup of a proof isn't really looked at in the further maths spec, except for proof by induction. And of course there's proof by contradiction in your normal maths, which you could look at. Otherwise there's not really much work in terms of what is called real analysis at university. So, pretty straightforward question there. Essentially, it just requires you to observe what the question's given you and find a foreseeable way to work with that information. And it's never going to be difficult, per se. Maybe induction will be difficult, but at least with induction, it's just in the inductive process is what it's called. You have to just spot a few things, and ultimately it kind of reduces the whole question down to the thing you want. And that is a skill that you have to develop over time with practicing these sorts of questions, which is true for any sort of maths. Now, I think I'll look at a follow-up question from our last video. So the question was, just a second. The transformation t in the plane consists of a reflection in the line y equals root 3x, followed by a rotation about 180 degrees about the origin, followed by a translation vector by the vector 2, 1, and the 3 by 3 matrix which represents t. And the answer to that question was, I'll just use a different colour. Just to simplify things down, not work through the question again, just to do the second part. The answer was a half minus root 3 over 2, or I should be labelling this part A, 2 minus root 3 over 2 minus a half, one, 0, 0, 1. So that was our 3 by 3 matrix from the previous video. Now, another question, most likely a follow-up from the previous question that we did in the last video, is show that there's no fixed points in the transformation T. So let's just rigorously define what this matrix is. This is our transformation T, consists of mini transformations, our rotation, translation, and reflection. Now, when a question asks you about invariant points, what it means by that is, if I were to apply this transformation to some set of points, x, y, and just to make these two matrices multiply each other, or allow for them to be multiplied with each other, I'm just going to add a 1. For a point to be invariant, if I apply this transformation t onto this set of points, I can say that there exists a set of points where if I apply this matrix to that, I will get the same points back. Now, what does this look like on a graph? If I have the xy plane over here, obviously I'll have some point, let's call it P, and it has coordinates xy. If I apply this transformation, okay, then that means that this point over here, and I'll call its transformation P prime, and I'll label it in green as well, will actually just transform onto itself. It's like you never applied the transformation is another way you could think about, think about this. So P prime, x prime, y prime. So the point will transform onto itself, i.e. it's an invariant point. Now, how do you show this? How do you show that this transformation in particular doesn't have any invariant points? And it has to do more so with the result that you get with this sort of calculation rather than the matrix itself. And the nice thing about this is that it does rely more on your GCSE knowledge than your A-level knowledge. So let's try and multiply these matrices out and see. And very nice thing, the maths that I've kind of laid out over here is the maths that we start with this sort of question. So let's multiply this out. So I'll get a half x minus root 3 over 2 plus 2 equals x for my first matrix, or sorry, first element. I'll actually just draw the matrices first just to illustrate what I'm doing. So this is a 3 by 3 matrix and this is a 3 by 1 matrix. If you remove the inner dimensions, you'll get a 3 by 1 matrix out. So if we multiply out our first row by our only column, we get for our first element, just going to make this a little bit bigger, a half x minus root 3 over 2y plus 2, which will be our first element. For our second element, we'll get minus root 3 over 2x minus a half y plus 1. For our last element, it's just going to be 0 times x, 0 times y, 1 times 1. So it's just our placeholder value 1, so that we can actually multiply these matrices together. Finally, this all equals x, y, and 1. Just like I did before with my previous question, what I'm going to do is I'm going to equate these coefficients together. I'm going to look at, sorry, not coefficients, elements. If I have the element here, half x minus root 3 over 2 plus 2, it will equal x, because this is the exact corresponding element on the left-hand side as it is on the right-hand side. That's what I was doing before when I was writing down the equation there, if you couldn't understand what I wrote. So I can just repeat this. I can kind of like, you know, transpose onwards. I can say this goes to that, my second element goes to y, and my last element, the third element, goes to 1. We can see a half x minus root 3 over 2 plus 2 equals x. And then minus root 3 over 2x minus a half y plus 1 equals y. And finally 1 equals 1, which is trivial. Now you have to show, okay, with these sets of equations, okay, and I say this is GCSE maths because essentially what you're working with over here are simultaneous equations. What you're showing is if I apply the matrix onto this point, I will get the same points back. This side and this side are the same because I've only done a calculation, okay, just to simplify things down. In essence, this side equals this side, but what you have to show that is that there's some inconsistencies here, okay? That for this point and this point, oh sorry, this element and this element, there's actually no solutions for the resulting simultaneous equations that you get, because ultimately what the question asks you is there's no invariant points, okay, and you have to show that. So what you should expect out of these simultaneous equations, because there's no invariant points, is that there's no points that you can get out of it. These simultaneous equations, they don't actually have a solution. So how can we show that? Well, what does it look like in 2D when two lines don't have a solution? It's when those two lines are parallel and they don't have the same y-intercept. So let's look at it this way. If this is my first equation and this is my second equation, this is just a draft, sort of a sketch. Clearly, if these two are parallel, and they have different y-intercepts, they're not going to meet. Either they're going to meet at one point or they're going to meet at all points. That means that what you should expect out of this, okay, let's say it says deduce whether or not this transformation has invariant points for general points x, y. Then you can expect two things out of this if there's the same gradient. Either the lines meet at all points, meaning the y-intercept is the same, or the lines meet at no points, which means the y-intercept is different. The key thing over here is that if the lines meet at all points, then there's a line of invariant points. So any point that kind of fulfills that condition or is part of that condition will be an invariant point. So enough of a lecture on that. I think we should start with the problem now. How can we show that this has the same gradient, okay, which is what we're looking for? And that's just simple rearrangement. We're just going to get y to be the subject so that we can judge whether these lines have a solution. I think I'm going to move y to this side so that I can get a positive y. So I get a half x minus x plus 2 equals root 3 over 2y. These two over here, they just go to a half x, or minus a half x, sorry. So minus a half x plus 2 equals root 3 over 2y. Multiplying both sides by 2 over root 3, so that I can get it for y. What I get is this expression. So the nice thing about this is that this is very easy to simplify. What you get in the end is, if you go through with your full simplification, obviously rationalizing the denominator and all that, although unnecessary, it is good practice. Plus 4 over root 3, so 4 root 3 over 3 equals y. That's our first equation. So I'll label that. Our second equation, pretty simple in fact to simplify. It's going to be minus root 3 over 2 x minus or plus 1 equals, if I move the half over, it's going to be 3 over 2y. Then it's the same thing again. I multiply both sides by the reciprocal of the coefficient of y. So I get 2 over 3 times minus root 3 over 2 x plus 1 equals y. Remember, 3 over 2 times 2 over 3 is just going to be 1. Any number multiplied by its reciprocal is 1. So in the end, what you get is minus root 3 over 3 x plus 2 over 3 equals y. Now it's just a case of observation. Is the gradient the same? Minus root 3 over 3. For equations 1 and 2, is it the same? Yes. Gradient is same. Now you have to ask the question, is the y-intercept the same? Because that is what distinguishes our question. That's what gives you the answer to the question. For equation 1, you have 4 root 3 over 3. For equation 2, you have 2 over 3. If I were to draw these lines, I've got this line over here. Okay, I'm going to actually label it 2 still. So if I draw this line, it'll be something of the sort like this. So this is line 2. And line 1 will look something like this. Clearly, because they have the same gradient, that they're parallel, just from your normal coordinate geometry or even just observation in your GCSE maths. Clearly these lines are parallel. They've got different lines of different intercepts, y-intercepts. So this is at 0, 2 over 3. And this one's at 0, 4 root 3 over 3. Thus, after giving a good explanation to the examiner, writing down, these lines have the same gradient but a different y-intercept. In other words, these two lines are parallel. Because they're parallel, either they meet at every point, i.e. the intercept is the same, or they meet at no points, i.e. their y-intercept is different. The case we have here is that the y-intercepts are different. That means that no points, or there's no solution to these two lines, or in other words, there is no invariant point under the transformation T. Hence, through deduction and a little bit of calculation, we have proven that there's no invariant points under this transformation. So that question right there requires you it requires you to have a little bit of observation skills. Kind of requires you to spot the right thing, and through that you have to deduce with a little bit of reasoning as to how you could prove what the question gives. And the nice thing is that the question kind of gives you what you're hoping for, and ultimately it will help you as an end goal for you to figure out your answer. Although a question isn't always that nice and you can't really expect it to give you a result that you're hoping for. Lastly, I think I'm going to cover a little bit of proof by induction. So this is an especially ugly looking question, I would say, because it's kind of riddled with terminology you might have never seen before, but in reality the process is quite simple. It's almost as simple as kind of thinking about it like dominoes, because that is what proof by induction is. And I'll explain what I mean in a second. The question is, show that there are no fixed points, sorry, that's the previous question. Just a second. Prove by mathematical induction that LHS equals RHS. So prove by mathematical induction that, and this is quite a mouthful to say, so I'll just write it up. This matrix So prove by mathematical induction that 0 to 0.50, this matrix, to the power of n is equal to a half plus minus 1 to the n over 2, 1 minus 1 to the n, a quarter minus 1 to the n divided by 4, a half plus minus 1 to the n divided by 2. So a mouthful of a question, very, very scary to look at first, but it only requires a bit of prerequisites, and again, just like with your previous questions, it requires a bit of observation and a little bit of discovery. So let's first of all look at what mathematical induction really means. And obviously fancy terminology, it kind of hides the fact that the actual process is really, really simple. It's like the simplest way to kind of illustrate this is dominoes, okay? And let's say I have one special case that I can prove for a statement X. So let's say I say that this statement X right here is true, always true. The way to prove that, obviously, is by brute forcing every possible number that you can get. Like, is this statement true for the number 1? And if I find it to be true, yeah, it's true, right? If I find it true for 2, it's true for 1 and 2, right? But it doesn't necessarily mean that it's true for 3 or 4 or 5 or 6 or all the way up, okay? So what the traditional method, okay, or what you usually call proof by exhaustion in your normal maths, okay, it's very, very inefficient for if you try to do like the set of all integers, or it'll be even more inefficient if you want to do the set of all real numbers, i.e. an uncountably infinite number of calculations that you'd have to do. So it's not feasible, not in any sense of the word. Unless, of course, you consider your cases differently. But that's kind of like a topic for another time. So clearly going on and on and on, I've represented my numbers as dominoes. Okay. To prove that X is true for, I should say, let's call this N. Let's say N is, or what I claim is that N is true for all positive integers, going up from 1 to infinity. Sorry, infinity is not a positive integer, but yeah. For the set of all positive integers, is this statement X true? And clearly the first thing that comes to mind, as I've been saying for the past 5 minutes, is check every number. 1, 2, 3, 4, 5, 6. No one's doing that. Instead, what you could do is it true for some value 1, maybe 2, maybe 3, maybe 4, maybe 5? The idea is you have to find it's true for one value. That value will usually be 1 in your case. So let's kind of color that in. So this statement X is true for n equals 1. Okay, I've kind of illustrated that. The next thing you want to do is you want to prove that it's true for 2, but in a sort of algebraic way. What you want to say is that for any number k, okay, so k could be anything. K is also a part of the positive integers. For any number n equals k, let's say, the statement also holds true. And that's your assumption. Then, using that assumption, what you can do is that I say that if this assumption is true, okay, I assume that this assumption is true, then the assumption must also be true for n equals k plus 1. But I say must be true for k plus 1. In reality, you have to prove that it's true for n equals k plus 1. And that is your inductive process. If you have n equals some general value k, okay, then you have to prove that a value more than that, a value 1 more than that, is going to be true. And that is your inductive process. Of course, this is a very flexible definition. You can have n equals k plus 2 maybe. That'd be able to prove it for every integer that's 2 more than k. But yeah, the inductive process that you go through is it true for a special case, like 1 or 2? Now, is it true for, well, now you have to assume that it's true for some general number k. And using that, could you prove that it's true for n equals k plus 1? And the conclusion you can draw from all that is that if this is true, okay, so if this is true, then what you can do is you can actually just substitute k equals 1 in, and then you say if k equals 1 is true, or sorry, n equals 1 is true, then n equals 2 is true, because k plus 1 is true, right? Same thing again, if n equals k is true, or n equals 2 is true, then n equals 3 has to be true, because n equals k plus 1 is always true if n equals k is true. Just like that, it cascades down all the way up to even infinity, right? For every possible integer value, or every possible positive integer value of n, you've thus shown that it's true for all of them, just by saying if it's true for n equals k, then it's true for n equals k plus 1, and then using your special case to substitute into k. So in a sense, it's kind of like I've made this one piece right here fall onto 2, which makes it true, fall onto 3, onto 4, in a set of infinite dominoes cascading down. So it's a very cool process. So enough with the lecture. How can we apply this process? And it's the same thing again and again and again. It is quite literally just you choosing one number for it, or finding one number for the statement to be true, and then going on from there, saying that n is true for any general number k, and then using that to prove that n equals k plus 1 is true. And that's where the inductive process comes in. So we have a proposition, first of all, that we have to write. Let proposition Pn be the statement that, and then you could just write that statement below. Now, what the thing I'm going to do now is say that there is a base case, or a value for which this proposition holds. Let's say that number is n equals 1. Base case. Now, substituting n equals 1 in to this expression, okay, and be sure to kind of use left-hand side and right-hand side instead of equating the two together, because you don't actually know that they're equal. So it's better for you to actually work with just the left-hand side and then the right-hand side, and then prove that the left-hand side equals the right-hand side in numerical value. That's just more mathematically correct, because essentially, if you equate them at the start, you're kind of already assuming that they're equal. And then you have to assume, if things go south, maybe, if you have maybe n equals 2 is true instead of n equals 1, then it's kind of like these two statements are actually false, so it's just mathematically cumbersome and less accurate. So it's better to work with just the left-hand side and the right-hand side, because then you can kind of work a little bit more simply. So we know that the left-hand side will just simplify down to this. Maybe I'll use fractions instead, just to kind of make the steps going down a little bit easier. Then you have your right-hand side, which will be this huge, ugly thing. It'll be a half plus minus 1 to the n, so it's going to be a half minus a half. 1 minus minus 1 to the n, so it's 1 minus minus 1. So a quarter, 0.5 over here, so that means that's a half. A quarter minus 1 to the n of a quarter, well, divided by 4, sorry. So that's just going to be a quarter minus a quarter. And then you have a half plus minus 1 over 2, because n equals 1. So it's just a half minus a half. Clearly a lot of arithmetic is involved in this as well. So again, just be very strong in your foundational concepts in maths, because ultimately the precision is what gets you through all of further mathematics and even normal mathematics. Clearly what we can see over here is that for at least one value for which, well, n equals 1, the left hand side and the right hand side do actually hold. We can thus say LHS equals RHS. Hence, n equals 1 holds for my proposition Pn. So that's our base case done, okay? We've kind of illustrated that for at least n equals 1, this holds. Okay, cool. Now you have to show that it holds for n equals k plus 1. And the way you do that is that, first of all, you have to assume that n equals k is true. What I mean by that is that you quite literally say, assume that for n equals k, Pn is always true. And I should be a little bit more rigorous over here, clearly, because n over here means integers. So actually, let me write that down. So for n is positive integer. Obviously, this sort of notation, you'll not see this notation a lot. Maybe in your second year normal maths you'll see it because of your domains and ranges, but it's not very often to see this. Well, it's not often that you'll see this notation in your A-levels. Okay, I'm just being a little bit mathematically rigorous over here by saying that n has to be a positive integer. Alright, so that's our base case done over here. Now what we have to assume is n equals k has to be true. So I'll just rub this off. What we say is that for, if I were to define this rigorously, it'll be for all k is also integer or positive integer, n equals k is true for Pn. So this statement right here is true. So just insert this sort of statement over here. I'm not bothered writing the whole thing out. So being mathematically rigorous, I say there's an integer n for which if it equals any integer k, positive integer k, then this statement is true. If I stop waving my hands at this and I actually write what the examiner expects you to, because this is a little bit beyond the syllabus, it's that assume n equals k is true for Pn. And what you do by that is just LHS equals 0 to a half 0 to the power of k, and RHS equals this matrix right here to the power of k, and LHS equals RHS. So this is where we stop waving our hands at the question. We kind of start with our inductive process. So that's what our proving n equals k plus 1 means. It's the inductive process of the question. So inductive process. Now, you have n equals k plus 1, which you have to prove is true if n equals k is true. And for this question especially, this is a very long and tedious process, I must say myself. What I will write is the statement that you should start with, then prove n equals k plus 1 is true if n equals k is true for Pn. So kind of writing this in like logical notation, n equals k implies that n equals k plus 1, and this is true and this is true. Obviously being a little bit lazy with the notation over here, but it doesn't really matter at AS or even A level, A2. So kind of just understand what the arrow means. If n equals k plus 1 or n equals k is true, then n equals k plus 1 is true. So how do we go about doing this process? And this process, this inductive process, differs from the type of inductive step that you're following. It kind of differs on the original context of the question. So imagine if this question was a series instead, and I had to apply an inductive process to that. The inductive step would be different because the underlying mathematics that I'm kind of trying to prove is also different. Okay. So first of all, you write out the statement. So I think I'll do it in green. My LHS will be equal to 0 to a half 0 to the power of k plus 1. My RHS would look like, and I will write it out this time, a half plus minus 1 to the k plus 1 over to 1 minus 1 to the k plus 1, then a quarter minus 1 to the k plus 1 over a quarter, or over 4, sorry, and a half plus minus 1 to the k plus 1 over 2. So this is the process that we land at, or the mathematics that we need to work with. The easiest way to show this is to actually define the left-hand side as some arbitrary matrix M. I'll just erase this side, just so that I can have a little bit more space. So we know for sure that LHS equals RHS for 0 to a half 0 to the power of k. So for n equals k, the proposition holds. We've already assumed that. What we have to do is we have to use that to our advantage and prove that this is true. Obviously, I think there's probably smarter ways to go about this, but this is the method of the mark scheme. For LHS, we can say that, actually I should say for our question, that the matrix M, I've just chosen an arbitrary letter, M matrix, makes a lot of sense, equals 0 to a half 0 to the power of k. And likewise, the matrix M also equals the right hand side, because for k it's true. So this huge thing over here, this also equals that. or rather I should say it's m to the power of k. Let's say m is actually the matrix 0 to 0.50. So it kind of ties into our inductive process. The step before, I don't think you could have done it with just m equals 0 to half 0. So sorry. So this matrix right here would actually be represented like mk plus 1. And so would this right here. Now, I think it's better for you to kind of work with this information yourself. Obviously right now I'd ask you to pause the video and try for yourself to prove that left hand side equals right hand side for m equals k, or m to the power of k plus 1. Because now you have enough information. You know that m to the power of k equals this, and this has to be true. But you don't know if m equals k plus 1 holds as well for the proposition Pn. So you have to use this to prove that. But how is that? How are you supposed to go about that process? And I'll give you a hint right now. You just have to multiply some things up. I'll give you an even bigger hint if you haven't done the question yet, or just can't be bothered pausing the video. You have to use your indices rules. So the nice thing about this right here is that mk, should underline, mk plus 1 is just the matrix mk times n. If I can prove for sure that this equals, or if I have assumed that this for sure is equal to each other, so the left hand side equals the right hand side for this case right here, then if I multiply both sides by the matrix M for k plus 1, or to get k plus 1, then this has to be true as well. Okay? Obviously you'll have a bunch of arithmetic to do here as well. But that is essentially the gist of it. You have to multiply the two sides over here, and by our rules of logic, if you multiply both sides by the same thing, then you should have both sides still equal each other by just our rules of algebra. Then if you find that that is true at the end of all of the multiplication that you do, and there is a bunch of tricky stuff in there as well, like you kind of have to consider -1 as an oscillating function, but in the end you should get that for m to the power of k, if m to the power of k is this matrix right here, and the left hand side equals the right hand side for n equals k, then for m equals k plus 1, which means that n equals k plus 1, the left hand side should also equal the right hand side, provided if this is true. So this implies that. Now, the last step in this very, very long question, I think the question was worth 7 marks, is write out your statement. So consider what information we have now. We have the information that the statement, or the proposition, is true for n equals 1. And if the statement is true for n equals k, then it's also true for n equals k plus 1. But hold on, I've kind of overlapped there. I've said n equals 1 is true, but if n equals k is true, then n equals k plus 1 is true. What if k equals 1? Then that means 2 is true. What if k equals 2? But 2 is true. That means that 3 has to be true. Likewise, 3 is true because, well, 4 is true because of 3 being true, 5 is true because of 4 being true, and you just kind of ascend up that ladder of every positive integer being true. And that is proof by induction. So it's a very, very powerful tool, very nice step. And to conclude your findings at the end of your whole inductive process is evaluating all of your findings, in the sense that, let's say since base case n equals 1 is true for Pn, and if n equals k is true, and and assuming n equals k is true, then n equals k plus 1 must also be true. Then for all integer values greater than or equal to 1 for n, Pn is true. Another way you could write this is since n equals 1 is true, since n equals 1 holds for Pn, and n equals k plus 1 holds for Pn, if n equals k holds, then by induction all subsequent integer values of n also hold. And at the end, just to be mathematically rigorous, you can just include your restrictions. There you go. That should be your inductive process. By far the most mathematically mature topic in further pure. Ultimately, it just involves you to, well, it involves more of your thinking than most other topics, because you kind of have to think a little bit more mathematically with proof by induction, at least with at the start, before it becomes more of a repetitive process. Obviously, the only calculation you really have to do in this sort of case is with the inductive process with n equals k plus 1. Another sort of process that you can follow with proof by induction is, or another topic that you can prove using proof by induction, which is very largely used, is sequences. But as far as I remember with the WJEC, I don't think there's a single sequences question that's popped up. With proof by induction, it's proof by divisibility that comes up usually, matrices, series, and although sequences is in the WJEC spec, proving sequences, it hasn't come up yet. So I don't think it will for a long time, at least until the spec changes, or maybe even before that. But yeah, I think that I could conclude at that. Thank you.